Hello, I'm Idot Sameret, and I'm going to walk you through this work about functional lower bound in algebraic proofs. This is a joint work with Thomas Hakoniemi and Nutan Limaye. Let's first discuss a high-level view of this work. What we want to achieve is a reduction from algebraic circuit complexity to proof complexity. Namely, we want to consider algebraic proof systems, usually strong ones, and we want to get hold of approaches to lower bound circuit, algebraic circuit, and to use them in proof complexity. And more specifically, this work is about studying lower bounds against strong propositional and algebraic propositional proof systems, and focusing specifically on a single major method for proving such lower bounds, which is called a functional lower bound method, which I will describe shortly. And what this work does is, focusing on this method, we expand the range of applications of this lower bound approach and show that basically all symmetric instances are hard, or some hardness for symmetric instances for a lot of proof systems, or certain strong algebraic proof systems. We also consider vector invariant polynomials as hard instances, and by this we achieve a lower bound over finite fields. We also strengthen considerably previous result of lower bound against constant depth algebraic proofs from multilinear proofs to non-multilinear proofs. At the end, we also expose the limitation of this technique, the functional lower bound approach, by showing that basically it will not lead to lower bound against propositional proofs with counting gates, namely AC0P Frege lower bounds. So first, let's discuss what is the object that we are interested in. So I'm not going to cover, of course, all proof systems and all proof complexity. I'm going to show you precisely what you need to know. What is the object that you need to understand for this work? And this is algebraic proofs. And I'm going to show a specific proof system of which you can consider, which actually subsume all different proof system we are interested in this work. Now, this will be the Nuss-Channel-Zatz refutation system. So what is it? We start from a set of axioms or constraints, Fi x equals 0, and we assume that this is a set of polynomial equations which is unsatisfiable over 0, 1. So a Nuss-Channel-Zatz refutation of this set of constraints is the following. It's a sum written like this of gi's times the fi's. Gi is any polynomial you wish to have. You sum it, and then you sum products, polynomial products of Boolean axioms. Xj squared minus xj, I call the Boolean axiom. Now you multiply this by some hj's and sum, and all this sum on the left-hand side equals as a polynomial identity to 1. Then this is what we call a Nuss-Channel-Zatz refutation of Fi. And if this is true, then there is no satisfying assignment. And for every Fi that is unsatisfiable, there will be such refutation. If it's not satisfiable, over 0, 1. So what are the different proof systems that we can define based on this Nuss-Channel-Zatz refutation? So Nuss-Channel-Zatz refutation is a single refutation system, but for simplicity, I'm going to describe different complexity measures that will basically constitute different proof systems all based on Nuss-Channel-Zatz. So if we consider this Nuss-Channel-Zatz refutation and consider the complexity measure of degree as is written on the left, then we define it as follows. It's the maximal degree of a polynomial out of gi's times fi or hi times the Boolean axiom. So that's what we call Null-Stellensatz degree. Now, monomial size is the size, but we just simply count the number of all possible distinct monomials in these summands, gi times fi and hi times Boolean axioms. This is the monomial size of a Null-Stellensatz refutation of some instance fi. Now, what is the circuit size? Now we start to consider a much stronger proof system. We can consider this instead of monomial size, we can consider writing these GIs and HJs as algebraic circuit of a certain circuit class. And this is where we consider circuit size and consider the total algebraic circuit size of this GI times FI and HI times Boolean axioms, which is called IPS for ideal proof system, introduced by Groucho and Pitassi. So it's the same, in some sense, the same proof system, just measured differently. We can also consider the following measure. It's a placeholder circuit size, which is almost the same as circuit size, only that I do not count the size of the axioms themselves, FI and Boolean axioms. And I call it a placeholder model for IPS, because I have placeholder for the axioms. I can write them just as a variable. And also I can consider restriction of circuit size by considering what I call CIPS, and for some technicality, lin. There should be some linearity here. It's not very important. And I call it CIPS lin, C circuit size, which is just measuring the algebraic circuit size only from the circuit class C. So GIFIs are written as circuit from class C, and the same for HI times the Boolean axiom. These are all the proof system you need to know. Now, I'm going to describe the functional lower bound method, which is one of the major methods allowing us to prove proof complexity lower bounds in the setup of strong algebraic proof systems. So I consider a refutation of a single 0-1 unsatisfiable axiom in this method. So this is important. You need only a single, you can use only a single unsatisfiable axiom, f equals 0. You also have the Boolean axioms, but those that are non-Boolean, it's only one instance, one polynomial, f equals 0. Now consider a Null-Stellensatz refutation of this f equals 0. It looks like g times f plus the sum of the product of the Boolean axioms equal 1 as a polynomial identity. Namely, all monomials, when you sum them all, they equal precisely 1. So this implies that if I consider x to be 0-1 assignment, all the Boolean axioms vanish, because under 0-1 assignment, they equal 0. So I get the following equation: g times f equal 1 for x Boolean. Now, this is already not a function, not a polynomial identity. It is what we call a functional identity, because it only is correct as a valuation over x, which are Boolean. So if I have this functional identity, I can also divide by f, because I know that f will never be 0 if f is unsatisfiable. So this division is fine, and I get g equal 1 over f for Boolean axioms. So now I have this functional identity, g equal 1 over f, and what I do is to conclude a CIPS lin lower bound for the instance f. It is sufficient to prove that the family of polynomials computing the function g, like this, which is r equal 1 over f, over 0-1 assignment, does not have small c circuits And that's how I get my lower bound for proofs. So now that we understood more or less what is the proof system we work with and what is the functional lower bound method, I'm going to describe the results and techniques. And these are the following. So first, I'm going to show you or explain two Nurstjern's degree lower bounds. So first is for symmetric instances. We show that basically they are hard for Nurstjern-Zatz. And the theorem is this: if f minus b is unsatisfiable and is also symmetric polynomial, namely invariant under permutation of variables, and it is of degree d in n variables, then a Nurstjern-Zatz refutation of this instance requires high degree, namely n plus 1 at least. And this generalizes for Spilka, myself, and Vigdorson 2021 result providing degree n lower bound only for degree 1 symmetric polynomials, namely the subset sum instance written in blue here. So we show it for every symmetric instance, more or less. No, actually, precisely, yes. Now, the idea is the following. It's not extremely hard. What we do is we consider a multilinearized product of two non-constant, namely not scalar monomials, of elementary symmetric polynomials whose sum of degree is at most n. And we show, that's by direct calculation, that such multilinearized product of two elementary symmetric polynomials must have a monomial which is different from one, namely of higher degree. So we will get a contradiction as I show you now. If I consider a Nurstjern-Zatz refutation, which looks like f minus b, that's the symmetric instance, times g, that's the proof, equals 1 modulo the Boolean axioms, then I can also write it as follows. Because I know that fx minus b is symmetric, I would also know that g is symmetric, because I know that g times f minus b equals 1. So it's not hard to show that g itself is symmetric. So the proof itself is symmetric. So basically, modulo the Boolean axioms, we get a product of two symmetric polynomials, of which I write for simplicity as a sum of elementary symmetric polynomial here. And what we get is the following, because if we assume, for the sake of contradiction, that the proof g is of low degree, namely the degree of g plus the degree of the instance, fx minus b, does not go above n, then I will know that here, on the left-hand side, there will be some monomial which is different than the constant monomial. But this is a multilinear polynomial which equals 1. So this is impossible because under multilinearity, there is only a unique multilinear polynomial that computes 1, which is the monomial 1. So I get a contradiction, assuming g is of a lower degree than b plus 1. So that was a kind of not very hard proof. We also have slightly more complicated proof for vector invariant polynomials. They are written as follows. The hard instance is going to be written as follow as one, as a product of the determinant of degree of dimension 2 by 2. And this is going to be a hard instance of degree n because we go over only the odd indices. But the number of variables is going to be 2n. And beta to be for this to be unsatisfiable, beta should be only, it's enough to assume it is different than 0, 1, and -1, because you can see that over Boolean assignments, this product must be either 0, 1, or -1. And this is also the reason why it works for finite fields. So our theorem shows that every Nullstellensatz refutation of this degree n instance will be of degree at least 2n. And this is interesting because it is a non-subset sum style hard instance that we can analyze its proof complexity. Now, after we understood the Nullstellensatz degree lower bounds, let's discuss size lower bounds. And how do we get the size lower bound? We get it via the idea or the technique based on lifting. Now, lifting is the following. The following idea. We take f, which is hard for Nullstellensatz degree, and we lift it in the sense that the variable now are going to be replaced by polynomials in pairwise distinct set of variables yi's. So under this lifting, we get an instance of which, if we knew a degree, a Nullstellensatz degree lower bound, now we will get a IPS size lower bound. And the idea is the following. I will show it in the next slide, but let's first discuss the actual results. And this is as follows. The base instance is symmetric f in Q1 to Qn. If we use this kind of lifting, namely expand the number of variables from n to 2n choose 2 and wij's, and we use this kind of lift from wij to zij, xi, xj, all three variables are Boolean, new Boolean variables. Then we can show an exponential lower bound on read-once ABP IPS lin, namely IPS refutation or Nullstellensatz refutation, where the refutation is written as read-once ABP, algebraic branching program. And this is over a large characteristic, which generalizes STOC24. For the invariant instance, this is the base case I showed you before, the degree lower bound. Now, if we use some lifting, we get the following lift, the following instance, which is resembling the original one, but with some extra variables. And we get read-once ABP IPS lin lower bounds, which are exponential 2 to the n, and multilinear formula IPS lin refutations with lower bound, which is quasi-polynomial, n to the log n. Both of these are in the placeholder model, namely the hard instance itself cannot be written with small read-once ABPs or multilinear formula, respectively. This work over finite fields of characteristic at least 4 or characteristic 0. Now, if we look at the base instance, which is the vanilla subset sum, just a sum of variables minus b equals 0, then we can do a substitution, which is a lifting like this, as shown in the last row, third row, fourth row, and using a non-trivial argument to match the so to speak, lopsided rank measured by Limaes, Srinivasan, and Tavenas, 21, we get a constant depth IPS lower bound of n to the omega log n, which is super polynomial, and the refutations are now can be up to O of log n individual degree. Now this improves the previous result, which was the same with the same hard instance, but with individual degree 1, namely multilinear refutations. This was showed by Govindasamy, Hakoniemi, and myself in 2022. And this is based on the work of, this result is based on a different proof of the Limaye, Srinivasan, and Tavenas lower bound by Amiredi, Garg, Kayal, Saha, and Thankay from last year. This works of a large characteristic. Now, let me explain very briefly how to get lifting, how this lifting paradigm works. And this is interesting as one technical contribution here, and also in previous works. So the goal, as I said, is to lower bound C circuit G such that G times F equal 1 over the Boolean cube. And what we know is only that there is a Nullstellensatz degree lower bound for G, which is linear in this case. So I have only a degree lower bound, but I want to get some size lower bound. Now, how do I get a size lower bound? Now I use machinery from algebraic circuit complexity. And in a lot of circuit classes that we use, we know that the size of a polynomial P in two pairwise disjoint distinct set of variables X and Y is lower bounded by the dimension of the following vector space, the vector space of polynomials P, X, and S, where S is a Boolean assignment substituting the Y variables. So if the dimension is high, the size of P in this certain circuit classes will be high as well. Now, to get from a degree to the size to the dimension lower bound, I'm going to use a lifting technique. So the lift is going to be some H with X and Y. So originally we have W, but we replaced them at H and XI, YI for different XI and YIs. And we let the new proof under the lift be G prime. Notice that if I have a proof of FW and I change the variables W with the lift H, Xi, Yi, the proof itself might also be different. So I now write it as G prime. It's not just the lift of G, it's a new polynomial, possibly. G prime, X, Y, and this is the new proof or refutation. It's G prime XY times F under the lift equal 1 over the Boolean cube. Now, what do I know? I'm going to show the following. I'm going to show that the dimension, that's our goal, of this lifted proof, G prime, is high. Now, we assume without loss of generality that G prime is multilinear. So the argument is this. We know that the dimension of a space of polynomials like this, G prime X under all possible Boolean assignment, is lower bounded by the number of distinct leading monomials when we fix some monomial ordering. That is known from computational algebra. So what we only need to show is that there is a lot of distinct leading monomials in this space. To do this, we need to, so to speak, isolate distinct leading monomials. And this is how we do this. I show you here an example. We take G prime X and take the characteristic vector of S, namely 1 where S is lit and 0 otherwise. And this is going to be, and this is my assumption here, that under this lifting, the lifting is defined so that this happens. Namely, under the assignment to the y's of the vector 1s, I collapse precisely to G under the X, in the X variables corresponding to the lit indices in S. That's my assumption on that's how I need to define the lifting function. Now, let's assume that this happens. So now I can use the degree lower bound. How? I'm going to show that the degree of G prime X, where Y's are substituted by 1s, is high. And it's going to be omega of the size of S. And that is because of my degree lower bound for G. Because under 1s, I assume that it collapses, G prime collapses to GXS. And I know here that the number of variables in GX restricted to S is precisely S. So I know by the degree lower bound that, that this will be the degree, which will mean that the leading term in G prime X1S has most of the variables Xi for I in S. So now if I take two different pairs, S1, S2, different Boolean assignment, I would know more or less that their leading term is going to be different because they will have different variables. And now, if I take enough of these pairs, I will get a lot of distinct leading monomials, and we can show that this is indeed exponential. And so the dimension of this vector space is going to be exponential, and we get the size lower bound on the proof, on the refutation of the lifted version of FW. So now the final result I want to mention is the barrier result. We say that a proof system is sufficiently strong if it admits an end introduction in the following sense. If I have Fi's as some proof lines, I can then derive the end of these Fi's in some representation of the end. This is a sufficiently strong proof system, and most natural proof system has this rule. Now, I'm also going to define Boolean instance. So in algebraic proofs, a lot of time I don't have Boolean instances in the sense that my constraints are polynomials such that even under Boolean assignments, they do not evaluate to 0, 1 values, but they can be 2, 3, and so forth. So Boolean instances are those polynomials that under the Boolean cube evaluate to 0, 1. So if I have a Boolean instance, which is unsatisfiable, or a set of polynomials that are all Boolean and they are unsatisfiable, like CNFs, then this I call a Boolean instance. And our theorem shows the following. The function lower bound alone cannot establish lower bounds for Boolean instances against any sufficiently strong proof system. And this will include a lot of natural ones, proof system like AC0P Frege and TC0 Frege, which are constant depth propositional proofs with counting gates. Now, I don't explain precisely how we got this, but it's not very difficult. Now, let's just turn to the conclusion. So we expanded on a major lower bound method against IPS, namely the functional lower bound method. We showed its limitations against Boolean instances. And now the good question is, what's left? So let's discuss briefly what's left for Boolean instances. Is there a hope for getting Boolean instances using IPS lower bound? I think there is some hope, because although the functional lower bound method as is cannot do this, it doesn't mean that some other reduction to a rank argument would not be helpful. Also, there are 3 other ways to use IPS lower bounds to get possibly Boolean instance hardness. So first, meta-complexity approach by Santanam and myself. This is mostly for conditional results. There's also the non-commutative approach, which consider non-commutative IPS. And there's also hard multiple approach, which consider which is a different approach than functional lower bound method. So all these might still work, and specifically some different reduction to a rank argument, I think might work in this setup. And that's it. Thank you very much for listening.